Good morning, students.
Morning,
Today,
ma'am.
good morning. Our today's topic is complements. Complements are used in digital computers for simplifying the logical operations. The r minus 1's complement of any number is defined as r minus 1 minus n, where r is the base. So if it is decimal number, the r is 10, and for binary r is 2, for octal it is 8, and hexadecimal it is 16. And n, small n, is the number of digits in the number, and capital N here is the number given. Okay, so what we do is we find r minus 1's complement by doing r power n minus 1 minus n, and r's complement of any number is obtained by r power n minus n, where r is the base, small n is the number of digits, and n is the number itself. The same can be written as r power n minus 1 minus n, the same formula, r power n minus 1 minus n plus 1. So in simple terms, we say that r's complement is finding r minus 1's complement and adding 1 to it. For a decimal number, r is 10, so r minus 1 is 9. So we can find 9's complement and 10's complement for a decimal number. We find 9's complement by finding 10 power n minus 1 minus n. So if suppose n is 2 here, when I find 10 power 2, it is 100. And if n is 3, 10 power 3 is 1000. If n is 4, 10 power 4 is 10,000. And so 10 power n minus 1 here becomes 100 minus 1 is 99, and here it becomes 1000 minus 1 is 999, and 10 power 4 minus 1 becomes 9999. Okay, so the value of this here, when the digit is 2, it is 99. When it is 3, 999, 3 nines. When it is 4, 4 nines. So simply we can say that to find the 9's complement of a decimal number, we need to subtract number from n nines. If I take a number 85, okay, and here n is 2. So to find 10 power n minus 1, I write 10 power 2. N is 2 here, minus 1 minus n. This is how we find the 9's complement. 10 power 2 is 100. 100 minus 1 is 99 minus 85. So it is 14. So 14 is the 9's complement of 85. This is 9's complement. And to find the 10's complement, we need to add 1 to the 9's complement. So 9's complement is 14. 14 plus 1 is 15. 15 is the 10's complement of the decimal number 85. And for a binary number, r is 2. So we can find the 2's complement and 1's complement for a binary number. In digital computers, complements are used during binary arithmetic. Okay, when we do binary arithmetic operations, these complements are generally used. So 1's complement of a binary number is 2 power n minus 1 minus n. So simply it is So here when n is 2, when the number of digits are 2, so when n is equal to 2 here, the number of digits are 2, we calculate 2 power n, that is 2 power 2 here, which is 4, and the binary equivalent of 4 is 100. And when n becomes 3, 2 power 3, that is equal to 8. The binary equivalent of 8 is 1000. N is equal to 4 when there are 4 binary bits. 2 power 4 we find, which is 16. The binary equivalent is 10000. So for binary we say that 2 power n is 1 followed by n zeros. And here we find 2 power n minus 1. So we need to subtract 1 from 2 power n. So 100 minus 1 is, we do the binary subtraction this way, 100 minus 1. Now this is bigger than this number, so we take borrow. Okay, here this becomes 0 and here it becomes 1 and 1, and the result is 1 with borrow 1, and here it is 1, it is 1 1. And when we subtract 1000 minus 1, it is, we take borrow from the next digit, next available digit, it is 0, and here all it becomes 1. And when we subtract this digit from the smaller to the bigger number, the result is 1 with the borrow 1. Okay, and here is 1 1 1. Here it is, the result is 1 1, and here it becomes 1 1 1, and here this is 1 1 1 1. So in simple terms we say that to find the ones complement of any binary number, subtract the number from n ones. If the number of digits are 2, subtract the binary number from 2 ones. If the number of digits are 3, subtract it from 3 ones. And if the number of digits are 4, subtract it from 4 ones. Let's take an example here. Let's say n is 1010. To find the ones complement, we write 2 power 4. It has 4 digits, minus 1 minus 1010, and 2 power 4 is 16, that is 1000, and minus 1 is 1111 minus 1010. When we subtract this, 1 1 minus 1010 1, and here it is 0 1 0, equal to 101. Here the given number is 1010, and the ones complement obtained is 0101. This is the ones complement. And to find the twos complement, we do the same thing, 2 power n minus 1 minus n plus 1. So we take the ones complement and add 1 to it. Ones complement of the given number is 101 plus 1. So when we add 101 plus 1 is 1 plus 1 is 1 0 in binary, 1 1. So it is 110. the 1's complement of 1010 is 101 and the 2's complement is 110. So we saw that the 1's complement of the number 1010 is 0101. It is obtained just by inverting the bits in the binary number, and 2's complement is of the number is adding 1 to this. So we get 1 plus 1 is 10110. So this is the 2's complement, 0110. To give another example, let's take another number 101100, a binary number 101100, and the 1's complement of this number is 010011, and the 2's complement is by adding 1 to this we get 101010. So this 10100 is the 2's complement of the number 101100. In the same way, for an octal number R is 8, so we can find the 7's complement and 8's complement for an octal number. Here when n is equal to 2, 8 power 2 is 64, 8 square minus 1 is 63. The octal equivalent of 63 is 77. And when n is equal to 3, 8 power 3, 512, and 8 power 3 minus 1 is 511. The octal equivalent is 777. When n is 4, 8 power 4, it is 4092, and the octal equivalent of 8 power 4 minus 1 is 7777. So we can simply say here that 7's complement of octal number can be obtained by subtracting the number from n 7's. When n is 2, 2 7's. When n is 3, 3 7's, and when n is 4, 4 7's. So here let's take an octal number 126. It is 8 power 3 minus 1 minus 126, 3 digits. So we subtract the number from 3 7's, 126, which is 651. 651 is the 7's complement of octal 126. This is 7's complement. And to find the 8's complement, we write the 7's complement of the octal number and we add 1 to this, so it is 652. We have seen different representations for digitally dealing with numbers. And to store the real numbers, there are two approaches to store the real numbers. By giving the binary point, binary point is the point that divides the integer part and the fractional part. So by giving the binary point a fixed position, or by employing a floating point notation. So the two approaches used are fixed point notation and floating. The number may be a signed number or an unsigned number. The three parts of fixed point number representation are the sign field, integer field, and the fractional field. So here, if it is the unsigned number has integer part and fraction part, whereas the signed fixed point number will have an additional field to store the sign bit. When a number is positive, the sign is represented by 0, and when the number is negative, the sign is represented by 1. And we can represent these numbers using a signed magnitude representation, 1's complement representation, and 2's complement representation. Generally, the 2's complement representation is preferred in computer systems because of the unambiguous property, and it is also easier for arithmetic computations. The floating point representation of a number has two parts. The first part represents the signed number called mantissa, and the second part of the number represents the position of the decimal point, and it is called exponent. These floating point numbers does not reserve a specific number of bits for the exponent or mantissa. Instead, they reserve some number of bits for the number called mantissa and some bits for exponent. And the nth bit here is designated as the signed bit. That denotes the sign of the number, whether it's positive or negative. So if we take a number plus 6132.739, the mantissa and the exponent part, so we can write it as plus 0.6132.739. The exponent is 4. Because I moved the decimal point to 4 digits, and in scientific notation, mantissa into r bar e. In this form, we can write it as 0. We can write it as 0.6132.739 into 10 power plus 4. So let's see how arithmetic addition and subtraction are done using this 2's complement system. Normally, when we perform ordinary arithmetic, if the signs of the numbers are same, we add the two numbers and we give the common sign. And if the signs are different, what we do, we subtract the smaller magnitude from the larger number and give the result the sign of the larger number, right? For example, let's take the numbers 6 and 13. If both are positive, plus 6 and plus 13, we add these two numbers and give the result plus sign. And if the number is, this is the first way, and the second option is if one number is positive, it may be either minus 6 plus 13, or the number may be like plus 6 and minus 13. So in these both cases, what we do is we take the bigger number, we subtract the smaller number from the bigger number, and we give the sign of the bigger number as the output. So in this case, we subtract 6 from 13. The result is 7, and the result would be plus 7. And in this case, we subtract 6 from 13, bigger number is 13, and we give the result is minus 7. And the other cases, both the numbers are negative. And if we have to do addition, if we have to perform addition on these numbers, we add, because the signs are the same, we add both the numbers and give the sign. The sign is minus, right? It's minus 19, and here it is plus 19. This process requires the comparison, then performing either addition or subtraction. Okay, we added the number 6 and 13 here in these both cases, and in this cases where the signs are different, we subtracted. So the operations we performed here are, we compared, comparison is one operation, and we perform addition, and we also did subtraction. To make this process simple, we use the 2's complement system. When we use 2's complement system, only what we need to do is we need to add and complement. So the two operations required there are complementation and addition. So the procedure becomes simple. The procedure to add the two numbers using 2's complement is just add the two numbers, and if the number is negative, if any number is negative, we need to find the 2's complement of that particular number. So the negative numbers must be in 2's complement form. And when we get the result, if the number is negative, means the nth bit is 1. Nth bit is 1 denotes the negative number, and if the nth bit is 0, that means the number is positive. So if the nth bit is 1, if the number is negative, that means it is in 2's complement form. Here let's perform a binary arithmetic addition by converting the negative number to its 2's complement form. Let's take the numbers. Okay, the first case, plus 6 and plus 13, and the 8-bit binary equivalent we write 1. It's a positive number, and 6 is 0, 1, 1, 0, and plus 13 is 1, 1, 0, 1. Here the most significant bit is the sign bit. As the numbers are positive here, the sign bits are 0. And when we add this, 0 plus 1 is binary addition, 1, 1. 1 plus 1 is 1, 0. 1 plus 1 is again 1, 0. 1, 0, 0, 0. So this is plus 6 plus 13. The result after addition is 0, 0, 0, 1, 0, 0, 1, 1. And now let's take the second case, plus 6 and minus 13. So in this case we have a negative number. 13 is a negative number. We write the binary equivalent of 6. It is 0, 0, 0, 0, 0, 1, 1, 0. And 13, the binary equivalent of 13 we wrote here, it is 0 0 0 0 1 1 1 1. And the 2's complement is, how we find the 2's complement of 13? First we write the 1's complement. It is just inverting the bits. 1 1 1 1 0 0 1 0, and adding 1 to this gives the 2's complement. So 1 1 0 0 1 1 1 1. This is the 2's complement of 13. As negative numbers need to be 2's complemented, we write this 2's complement of 13 1 1 1 1 0 0 1 1. The operations we perform are complementation and addition. It is 1 1 plus 1 is 1 0, again 1 0 1 1 1 1 1. This is the result of plus 6 minus 13. And here the sign bit says it is a negative number. That means the number is in 2's complement form. So here this is the binary equivalent of plus 19, and this is the binary equivalent of minus 7. To check it, let's again find the 2's complement of this number. We need to get plus 7. So 1 1 1 1 1 0 0 1. The 1's complement is 1 1 0 0 0 0 0 1 1 0. Then 2's complement is, adding 1 to this, we get 1 1 1 0 0 0 0 0. So this is equal to plus 7. Okay, so this shows that this number is the 2's complement of 7. So it is minus 7. And the third case, is minus 6 plus 13. So the negative number here is minus 6. Now 6 need to be complemented, 2's complemented. 6 is 0 0 0 0 0 1 1 0, and when we complement the bits, it is 1 1 1 1 1 0 0 1. 1's complement of 6. And the 2's complement is, we add 1 to this, 1 0 0 1 1 1 1 1. So this is the 2's complement of 6. We write the 2's complement of 6 here, 1 1 1 1 1 0 1 0, and 13 as it is. We don't find the complement here. 0 0 0 0 1 1 0 1. When we add this, 1 1 1 1 0 1 0 1 0 1 0 1 0 1. The carry out of the sign bit will be discarded here. So the result is 0 0 0 0 0 1 1 1. The sign bit here is 0, so it is a positive number, and the result is plus 7. Let's take the fourth case. Both the numbers are negative, minus 6 minus 13. So in this case, as the two numbers are negative, we need to find the 2's complement of both the numbers. 2's complement of 6 is this, we already found it, and 2's complement of 13 is here, 1 1 1 1 0 0 1 1. So when we add both these numbers, 1 1 1 1 1 0 1 0 is the 2's complement of 6, and the 2's complement of 13 is 1 1 1 1 0 0 1 1. When we add these two, we get 1 1 0 1 1 1 0 1 1 1 plus 1 plus 1 is 1 1, and here again 1 plus 1 plus 1 is 1 1, again 1 1. We have a carry out of the sign bit. The sign bit here is 1, so that means this is a negative number. Here to find this number, we take the 2's complement. So first 1's complement is 0 0 0 1 0 0 1 0, and when we add 1 to this, 1 1 0 0 1 0 0 0. So it is 19, positive 19. So this is complement of 19 minus 19. To perform arithmetic subtraction, the procedure is: take the 2's complement of the subtrahend, add it to the minuend, and a carry out of the, here also the carry out of the sign bit is discarded. Okay, the procedure is: take the 2's complement of the subtrahend, add it to the minuend, and discard the carry that you get out of the sign bit. So let's take an example: minus 6 minus 13. So what is minus 6? 6 is 0 0 0 0 0 1 1 0, and the 2's complement of 6 is minus 6. So it is 1 1 1 1 1 0 1 0. Minus 6 is 1 1 1 1 1 0 1 0, and minus 13 is the complement of 13, that is 1 1 1 1 0 0 1 1. Now the procedure says: take the 2's complement of the subtrahend, that is 13, and add it to the minuend. We need to take the 2's complement of minus 13. It is 1's complement is 0 0 0 0 1 1 0 0, and when we add 1, we get 1 0 1 1 0 0 0 0. So this is the 2's complement of minus 13. We add it to the minuend. Minuend is minus 6 already. So to add this, 0 0 0 0 1 1 0 1. We get 1 1 1 1 0 1 0 1 0 1 0 1 0. The carry out of the sign bit here 1, which is discarded, and the result is a positive number. The sign bit is 0 here. It is 0 1 1 1 is plus 7. This is how arithmetic addition and subtraction are performed using 2's complement. Here are few exercises to do based on the topic what we have discussed today. Find the 9's and 10's complement of the given numbers. Here the second number has 6 zeros. It's not a binary number. You have to find the 9's and 10's complement. And the second question is: find the 1's and 2's complement of the given binary numbers. And the third question is: perform the arithmetic operations in binary using signed 2's complement representation for negative numbers in the same way how we did for 6 and 13. Okay, you do the same, finding the 2's complement for the negative numbers and adding it to the other number. And the fourth question is: performing arithmetic operations on the given numbers with using signed 10's complement representation for negative numbers. Good morning, students. Today,
Morning, ma'am.
good morning.